Hello, this is Sadbir Malli. This is our first video of our course Linear Algebra. In this video, we will review vectors. Vector is a physical quantity that has both magnitude and direction. For example, a car is traveling south along a freeway at 17 miles per hour is a vector quantity because it also tell us what is the direction in which the car is heading to, and also to give us the speed of the car, which is a 17 mile per hour. So this quantity will be represented by two different things, directions and the magnitude. So we will call this as a vector. Notation, sometimes we represent the vector as u and arrow on the top. For example, F vector represent the vector of force, meaning they both have a magnitude and a direction. Here is one quiz problem. Pause the video for 1 and 2 minutes and answer this problem. Which one of this quantity is a vector quantity? Graphically representation of vector. In order to represent a vector, we need to know where is the tail of the vector and where is the head of the vector and what is the magnitude of the vector. Suppose the tail is at point A, whose coordinate in Cartesian system is x1, y1, and the head of this vector is at the point B, whose coordinate is a x2, y2. So this is a point B. Then the magnitude of this vector, let's suppose this is a vector V, will be the square root of x2 minus x1 plus y2 minus y1 square. That is the distance formula between the point A and B. This is the magnitude of the vector. How to represent that vector graphically in the xy plane? All we need to do is we need to draw the point x1, y1. That is the tail of the vector, and then we will draw the vector x2, y2, which is the head of the vector, and then this is how we will represent. Also, to calculate the vector A, B in a Cartesian system, what we do is we subtract the point, the head of the vector, from the tail of the vector, and the second head of the vector to the tail of the vector. So this is the representation of the vector. In Cartesian planes, you can move the vector without changing the magnitude and direction, and this will be a same vector. For example, if I place the tail of the vector as here, and without changing the direction of the vector, I just draw the similar a vector with the same length, whatever the length was the original vector. So this vector will be the same. So changing the position of the vector in a Cartesian coordinator will not change the dynamics of the problem. For example, we draw a vector v 3, 2 in a Cartesian plane as taking the tail at 0, 0 at the origin, and head of the vector is 3, 2. In order to find the magnitude of such a vector is easier when the tail is at the point 0, 0. So the magnitude of this vector will be simply the square of its component and then adding them and taking the square root. So the magnitude of this vector is 13 in this case. Now we will study some operation on vector. Scalar multiplication. If we multiply a vector by a scalar or a number, it will not change the direction of the vector. In fact, it will increase or decrease the size of the vector. If the number is bigger than 1, let's suppose it's equal to 2, it will double the size of the vector. If you multiply by a negative number, it will double the size of the vector as well, but it will reverse the direction of the vector. For example, if the vector is written in a Cartesian system, so where is v, where the head of the vector is at 3, 2, and you want to multiply that by a scalar, all you need to do is to multiply each component of the vector by that scalar. For example, if we multiply 2 here to the vector, all you need to do is you multiply this 2 to 3, and then you multiply that 2 to 4. So that's why you get 2v vector 6 comma 4. And if you're multiplying by a negative 1, all you need to do is you need to multiply the negative 1 to these two components of the vector. Next is the addition. So there is a two way you can calculate the addition of the vector. So let's suppose you have a vector uh, u, and then there is a vector v. The one way to calculate is by using the parallelogram law. So you take the vector u, you move the vector v where the tail of the vector u is, and then you draw a parallelogram. Then the addition of this vector will be this vector, which is the diagonal of the parallelogram. So this will be u plus v vector. So this is a parallelogram. Another way of calculating the addition is if you take that vector u, and now the vector v, you move on the head of the vector u. So let's say this is a vector v. So this is in this direction, this is going this direction. The resultant vector, which is a u plus v, will be this vector now, which is the third side of the triangle. That will be u plus v vector. And the direction of this vector will be in this direction, which is the opposite to the direction of u and v. For example, if your vector are written in a Cartesian system, so you have a vector u 3 comma 1 and you have a vector v minus 1 comma 1, the addition of these vectors are simply adding the exponent of these two vectors. So here 3 plus negative 1 is a 2, or 1 plus 1 is a 2. And you can see that this will, if you plot these vectors in a Cartesian system, they will both satisfy the parallelogram law as well as they will satisfy the triangle law. So like if I draw this vector 3 comma 1, so this is my 3 comma 1 vector. It's a 3 unit and 1 unit above. So this is the head is a 3 comma 1. Negative 1, x is a negative 1, y is a 1 is somewhere here. So this is vector is a negative 1 comma 1. Then according to the parallelogram law, this vector will be the diagonal of this parallelogram, which is simply this vector, which is as 2 comma 2, as we calculated when the vector is written in a Cartesian system. So as you can see that if the vector is written in a Cartesian system, it's easier to add and subtract the vector. What is a linear combination? The linear combination of two vectors is when you use the multiplication and addition operation same time. So here is an example of a linear combination 2u plus 3v, where the vector 2 time of vector u added in the 3 time of vector v. So let's calculate this, what this linear combination is. This is a 2 time vector u, which is a 3 comma 1, and it is added into the 3 time vector v, which is a negative 1 comma 1. So this will be simply a vector which is a 3 time 2 is a 6, and this is a minus added into 3, and this is a 2 plus add, this is a 3 time 1 is 3. So if we calculate this linear combination, this will be a 3 comma 5. So this is our linear combination when you have multiplication and addition operation same time. The next is how to calculate the dot product between the two vectors. So a dot product, when you multiply a vector u to v, it gives you a scalar. And this is how you calculate it if the vectors are written in a Cartesian system. So you multiply the first exponent of vector this to the first exponent of the vector v, and then you multiply the first exponent of the u vector to the first exponent of v. So this is the formula for when the vectors are written in a Cartesian system. If the vectors are not written in a Cartesian system, then the dot product is given by the magnitude of u, magnitude of v times the cosine of theta, which is the where the theta is the angle between them. So here I have two vectors u and v, which are written in a Cartesian system. So the dot product of these vectors are easy to calculate. So u dot v will be 3 times 2, which is a 6, and 2 times 1, which is a 2. So this is a 8. And let's suppose I want to use the second formula, but I can only use the second formula if I know what is the angle between these two vectors. In this case, with the angle is not given, so I will use the first formula. Here is another definition which is depend on the dot product. Two vector u and v are perpendicular if and only if the dot product between these two vectors are 0. For example, this vector u, which is a 1 comma 2, and vector v, which is a negative 2 comma 1, they are perpendicular because their dot product is 0. Here I have the second quiz problem. Find a vector which is perpendicular to 3 comma 2 and has magnitude 2. Pause the video for 1 or 2 minutes and work on this problem. This is the end of this video. I will see you in the next video. Bye for now. Thank you for watching.